Gaze into the deepest image ever taken of our universe, the Hubble Ultra Deep Field. In that single patch of sky, smaller than a grain of sand held at arm's length, are thousands of galaxies, each containing billions of stars. It's a humbling, almost overwhelming sight that makes you wonder, in a cosmos so vast and ancient, what secrets are still waiting to be uncovered. We've sent probes to distant planets, built telescopes that peer back in time, and walked on the surface of the moon, yet somehow, it feels like we're only scratching the surface. What if everything we think we know about space is just the beginning of a much larger, much stranger story? Today, we're setting off on a journey through some of the most mind-bending, awe-inspiring, and downright peculiar moments in the history of space exploration. From mysterious signals and cosmic coincidences to engineering marvels and scientific surprises, we'll uncover 30 facts that challenge what we thought was possible and ignite that childlike wonder we all felt the first time we looked up at the stars. This isn't just a list of trivia. It's an invitation to see the universe through new eyes, to marvel at human ingenuity, and to reconnect with the curiosity that drives us to explore in the first place. So whether you're a long-time space enthusiast or just someone who occasionally glances up at the night sky and wonders what's out there, you're in the right place. Together, we'll venture beyond the textbooks and headlines into a world where reality often feels stranger than fiction. A place where astronauts hear mysterious music on the far side of the moon, where planets rain diamonds, and where silence speaks louder than words. Get ready for a ride through the weird and the wonderful, because space, as it turns out, has been keeping secrets, and today we're pulling back the curtain. Let's kick things off by shattering one of the most delicious myths in all of space exploration. If you've ever been to a science museum, you've almost certainly seen it, that brittle, chalky, yet strangely appealing brick of astronaut ice cream. It's been presented for decades as a genuine taste of spaceflight, a crunchy souvenir of human ingenuity. But here's the wonderfully weird truth: it's a complete fabrication. No astronaut has ever officially consumed this freeze-dried treat while orbiting the Earth or walking on the moon. The story begins with good intentions. The stuff is real. It's called Neapolitan ice cream, and it was indeed developed by a company called Whirlpool Corporation under contract for NASA during the Apollo era. The idea was revolutionary. Use freeze-drying to remove all the water from the ice cream, leaving behind a lightweight, shelf-stable product that wouldn't melt. The problem wasn't the taste or the science behind it. It was the simple, pesky laws of physics. In the microgravity environment of a spacecraft, everything floats, including crumbs. That crunchy texture we experience on Earth becomes a cloud of tiny, destructive particles in space, capable of floating into an astronaut's eyes, nose, or, most dangerously, into the intricate vents and sensitive electronic equipment that keep the spacecraft functioning. So what did the Apollo crews actually eat? Their menus were filled with rehydratable foods in sealed pouches, everything from spaghetti and meatballs to shrimp cocktail. But the true, crumb-free champion of space cuisine, the snack that has earned a permanent place aboard the International Space Station, is something far more humble: the tortilla. Mission planners realized that bread creates too many crumbs, but a soft flour tortilla, it's perfect. It can be used to make sandwiches, doesn't produce loose debris, and even has a long shelf life. The love for tortillas in space is so real that NASA even had to develop a special, longer-lasting recipe to prevent them from molding on long-duration missions. The persistence of the astronaut ice cream myth is a fascinating case of marketing meeting nostalgia. While it never made it to the final menu, it was a tangible product that companies could sell to a public eager to connect with the glory of the space race. It allowed people on Earth to, in a very small way, feel like they were participating. So the next time you see that familiar foil pouch in a gift shop, you can appreciate it not as a relic of space travel, but as a quirky artifact of our own imagination, a symbol of our desire to reach for the stars, even if it's just with a sweet, crumbly snack. Moving from the world of imagined treats to a sensory experience that was utterly real for the Apollo astronauts, we come to one of the most unexpected and strangely visceral facts about lunar exploration. After hours of bouncing across the brilliant gray landscape, these pioneers would clamber back into the cramped confines of the lunar module, seal the hatch, and begin to repressurize the cabin. As they finally removed their helmets, they were hit not by silence but by a smell. A potent, acrid odor clung to their suits, their gloves, and the dust that coated every surface. They struggled to describe it, but the most common comparison was to the familiar scent of spent gunpowder, like the air after a fireworks display, with some adding notes of wet ashes or a burnt match. This was the smell of the moon itself, and it presented a fascinating scientific puzzle. The lunar dust, or regolith, is the result of billions of years of meteorite and micrometeorite impacts constantly fracturing and melting the bedrock. It's not soil as we know it, it's a sharp, glassy, and chemically reactive powder, and it had been sitting in a perfect vacuum, completely untouched by oxygen or moisture for eons. The leading theory behind the gunpowder smell points directly to this sudden and dramatic change in environment. When the astronauts tracked the dust into the cabin, those tiny, reactive particles were for the first time being exposed to the moist, oxygen-rich air inside the lunar module. In essence, the dust was undergoing a rapid process of oxidation, a very slow-motion combustion on the surface of each particle, and it was this chemical reaction that released the distinctive odor. Think of it like striking a match. The match head contains all the potential for that reaction, but it needs the friction of the strike and the oxygen in the air to actually ignite. The lunar dust was like a trillion unstruck matches just waiting. The cabin air provided the final ingredient, and the astronauts' noses were there to detect the result. This strange phenomenon highlights a fundamental challenge of exploring other worlds. We can't ever truly experience them in their natural state. The moment we interact with an alien environment, we change it, and it in turn interacts with us in ways we can't always predict. The moon's true scent, in the absolute silence of its vacuum, remains a mystery we can only infer from the echo of its reaction with our own world. That lingering scent of oxidation, a final sensory gift from the moon, serves as a poignant reminder that our explorations leave a mark. But what about the machines we send on these incredible journeys? Their stories don't always end with a heroic return. Sometimes their final chapter is written on the very alien soil they were sent to study. In the vastness of our solar system, there exists a quiet, windswept cemetery on Mars. This isn't a graveyard with headstones and markers as we know them. It's a region on the Red Planet, a specific area within the immense plain of Utopia Planitia that has become the final resting place for several of our robotic explorers. The most famous resident of this Martian memorial is undoubtedly NASA's Spirit rover. For 6 incredible years, far outliving its original 90-day mission, Spirit traversed the landscape, analyzing rocks, taking breathtaking panoramas, and fundamentally reshaping our understanding of the planet's history. Its mission finally ended in 2010, not because its systems failed, but because it became trapped in a patch of soft, sandy soil. Despite exhaustive efforts to free it, Spirit was ultimately declared a stationary science platform before falling silent for good. It sits there still, a silent testament to human ingenuity and perseverance, but Spirit is not alone. This same region holds the remains of other pioneers. The United Kingdom's Beagle 2 lander, which arrived on Mars on Christmas Day 2003, mysteriously vanished without a trace after its separation from the European Space Agency's Mars Express orbiter. For over a decade, its fate was one of the great unsolved mysteries of Mars exploration. Then, in 2015, NASA Mars Reconnaissance Orbiter spotted it. The stunning high-resolution images revealed that Beagle 2 had actually landed successfully, a remarkable achievement in itself. Its failure was tragically simple. One of its 4 solar panels had failed to fully deploy, blocking the antenna and preventing the lander from ever phoning home. It sits there, intact but silent, a success story that we simply couldn't hear for 12 long years. This Martian cemetery is more than a collection of failed machinery. It's a hallowed ground of discovery. Each silent spacecraft represents a monumental leap of faith, a bundle of hope and ambition launched from our world toward another. They are the physical embodiment of our curiosity, and even in their silence, they continue to teach us. They show us the immense challenges of interplanetary travel, where a single misstep, a rogue rock, or a patch of tricky sand can end a mission. But they also represent a legacy of incredible success. The data they sent back, right up to their final moments, has been invaluable. They are the pathfinders, the scouts who paved the way for the more advanced rovers like Curiosity and Perseverance that now follow in their tracks. They remind us that in the grand endeavor of exploration, even endings contribute to new beginnings. This peculiar physical reality is one of the most intimate and humanizing challenges of living off-world. On Earth, crying is a release. Grief, frustration, overwhelming joy. These emotions find a physical outlet in tears that roll down our cheeks, a process so natural we never give it a second thought. But in the microgravity environment of orbit, that fundamental human experience is completely rewritten. Without gravity to pull them downward, tears simply do not fall. Instead, the saline fluid secreted by your tear glands has nowhere to go. It begins to accumulate right there in the eye, coalescing into a single, ever-growing bubble that clings to your eyeball and the surrounding socket. What starts as a simple welling of the eyes quickly becomes a large, quivering globe of liquid. Astronauts describe the sensation as incredibly strange and distinctly unpleasant. The growing bubble can cause a stinging sensation as the salt content of the tears is held directly against the eye rather than being whisked away. It creates a blurred, watery mess that obscures vision, and if you try to blink, the result isn't relief but a chaotic dispersal. The force of your eyelid can break the large bubble into dozens of smaller, free-floating droplets of tears, which then drift around the cabin. You're left not with a cathartic release, but with a face full of stinging, salty water droplets and the practical problem of having to corral them all with a towel to prevent them from getting into equipment or another crew member's eyes. This phenomenon forces astronauts to adopt a different emotional response mechanism. Many report consciously suppressing the urge to cry, not out of stoicism, but out of sheer practicality. The physical discomfort and messy aftermath actively discourage the act. Instead, they might channel that emotional energy into intense physical exercise on the station's equipment, lose themselves in the breathtaking view of Earth from the cupola, or engage in a focused conversation with a colleague or a psychologist on the ground. It highlights a profound truth about long-duration spaceflight. The greatest challenges aren't always the colossal ones like radiation or rocket science. Sometimes they are the quiet, personal moments where your own body, and the very ways it expresses humanity, are fundamentally at odds with the environment you're in. The inability to cry properly is a powerful reminder that in space, even our most innate human behaviors require reinvention. And speaking of the journeys we've launched into the cosmos, none carry a more profound or poetic message than the twin Voyager probes. In 1977, as they began their grand tour of the outer planets, they carried with them more than just instruments for scientific discovery. Attached to each spacecraft is a golden 12-inch phonograph record, a time capsule intended for any intelligent life that might one day find them, long after humanity and Earth are gone. This isn't science fiction, it's a real, physical message cast adrift in the ocean of space, and its contents are a stunningly optimistic snapshot of our world. The brainchild of a committee led by the visionary astronomer Carl Sagan, the Golden Record is a meticulously curated collection of sounds and images meant to tell the story of Earth and its inhabitants. Imagine an alien civilization, billions of years in the future, somehow intercepting this small, silent craft. If they can decipher the instructions symbolically etched onto the record's protective aluminum cover, they would be treated to a sensory experience of our planet. They would hear the roar of a volcano, the gentle patter of rain, the crash of ocean waves, and the sounds of life, the songs of whales, the chatter of chimpanzees, and even the restless footfalls of a human heartbeat. But the true soul of the record is its music. The selection is a breathtakingly diverse choir of human expression, a mix carefully chosen to represent the entire globe. An alien listener would hear the soaring precision of Bach's Brandenburg Concerto, the haunting beauty of a Navajo night chant, the driving rhythm of Seneganian percussion, and the raw, joyful energy of Chuck Berry's Johnny B. Good. It is a statement that intelligence is not just about logic and science, but about art, emotion, and the universal language of rhythm and melody. The record also carries spoken greetings in 55 languages, from ancient Akkadian to modern Wu Chinese. Each message is a simple hello, a wave from across the void. But perhaps the most moving inclusion is a silent one, 115 images encoded in analog form on the record's surface. These pictures tell a visual story of our biology, our anatomy, our planet's diversity, and our technological achievements. They show diagrams of DNA, photographs of a nursing mother, scenes of city traffic, and the faint, hopeful image of a single sunbeam illuminating the Earth. The cover itself provides the key to the treasure, with intricate diagrams that use the precise timing of 14 pulsars, cosmic lighthouses, to pinpoint our sun's location in the galaxy and provide a universal map back to our tiny, pale blue dot. The Voyager Golden Record is far more than a scientific experiment. It is one of the most profound philosophical statements humanity has ever made. It represents a boundless optimism, a belief that our flaws and conflicts are not our entirety, and that there is something beautiful and worthy of preservation in the human experience. It is a message in a bottle launched into the cosmic sea, a testament to the idea that even in the vast, silent darkness, it is worth saying, "We were here." And as we send our messages and our machines out into the void, we inevitably confront one of the most profound questions of all. Could life itself make that journey? Could a living organism survive the brutal transit between worlds? The answer, astonishingly, is yes, and we know this because we've found one right here on Earth. Meet Deinococcus radiodurans, a humble bacterium that holds the title of the toughest known organism in the universe. This microbe is so incredibly resilient that scientists have affectionately dubbed it Conan the Bacterium, and its superpowers fundamentally reshape our understanding of life's potential. In a series of experiments that sound like they were drafted for a superhero origin story, scientists placed colonies of this bacteria on the outside of the International Space Station on the European Space Agency's Expose-E platform. For well over a year, these tiny organisms were subjected to the most hostile environment imaginable. The complete vacuum of space, temperatures swinging from freezing to scorching as they passed in and out of sunlight, and a constant, unshielded bombardment of cosmic and solar ultraviolet radiation intense enough to shred DNA. When the samples were finally brought back inside and rehydrated, the results were staggering. While many of the outer layers of bacteria were, unsurprisingly, utterly destroyed, those sheltered just millimeters beneath them woke up. They not only survived but went on to repair their own ravaged DNA and thrive, completely unscathed by their interstellar ordeal. So how does it do it? The secret lies in a DNA repair toolkit so efficient it borders on science fiction. Deinococcus radiodurans possesses multiple copies of its genome and chromosome, essentially keeping backup copies of its entire genetic blueprint. when its DNA is shattered by radiation, a fate that will be instantly fatal to almost any other life form, these specialized cellular mechanisms swing into action. They quickly identify the broken fragments, use the intact copies as a reference guide, and meticulously stitch the entire genome back together, often within a matter of hours. It's like having a book that can instantly reassemble itself after being put through a shredder, as long as another intact copy of the book is sitting right next to it. This incredible hardiness has massive implications for a theory known as panspermia, the idea that life could be distributed throughout the cosmos by hitchhiking on asteroids, comets, or spacecraft. If a microbe like Conan the bacterium can survive years on the exterior of a space rock, then the concept of life traveling from Mars to Earth, or even between star systems, is no longer just a fringe idea. It becomes a plausible, testable hypothesis. An impact on a life-bearing world like early Mars could have ejected rocky debris into space. If that debris contained resilient extremophiles sheltered within its interior, they could have endured the long journey through space before eventually crashing into a young, welcoming Earth, potentially seeding our planet with the first ingredients of life. But this amazing possibility also presents a formidable challenge for space agencies, one known as planetary protection. The same resilience that allows life to potentially spread naturally also means that our own spacecraft could inadvertently become the vector. Every rover, lander, and probe we send to another world is meticulously sterilized to prevent any terrestrial microbes from contaminating that pristine environment. We have an ethical and scientific obligation to ensure we are not the ones responsible for planting Earth's life on Mars or Europa, because if we ever did find life there, we would need to be absolutely certain we didn't bring it with us. The existence of Conan the bacterium makes this cleaning process infinitely more difficult. It forces us to ask not just if life could be out there, but how carefully we must act to preserve the natural stories of other worlds, ensuring our own curiosity doesn't accidentally write the first chapter. And speaking of monumental challenges, let's talk about the unsung hero of the launch complex, a machine so colossal and deliberate that it makes a snail's pace look like a sprint. Picture the final, tense hours before a rocket launch. The air crackles with anticipation, engineers are making last-minute checks, and the world's most powerful machine is poised for its journey. But to get there, it first had to take the slowest ride of its life, carried by NASA, a legendary crawler transporter. These are the largest self-powered land vehicles ever built, and seeing one in motion is a lesson in breathtaking scale. Each one is the size of a baseball in field, over 130 feet long and 115 feet wide. Its weight is almost incomprehensible, a staggering 6 million pounds for the crawler itself. But that's just the beginning. When it gets to work, it slowly maneuvers under the massive mobile launcher, the structure that holds the rocket upright, and lifts the entire assembly onto its back. With a Space Launch System rocket and its mobile launcher secured on top, the total weight this mechanical titan carries can exceed 17 million pounds. That's heavier than a fully loaded aircraft carrier, and it's all resting on this one vehicle. Now for those jaw-dropping speed stats. When carrying its priceless, world-changing cargo, the crawler transporter has a top speed of exactly 1 mile per hour. If it's making a return trip empty, it can unleash its full, unbridled power to reach a dizzying 2 miles per hour. To put that in truly humbling perspective, the common garden snail has an average speed of about 0.03 miles per hour. Our mighty crawler, when loaded, is only about 30 times faster than a snail. This isn't a design flaw, it's an absolute necessity. The journey from the vehicle assembly building to the launch pad is a 4-mile trip that takes over 8 hours. Every inch of that path must be traversed with unimaginable precision. The vehicle doesn't just drive, it levels itself continuously with a hydraulic system so sensitive it can keep the rocket perfectly vertical. ensuring that the multi-billion-dollar payload on its back doesn't experience even a fraction of a degree of tilt that could cause catastrophic stress. The entire operation is a masterclass in controlled power. The crawler is driven by a team of over 24 engineers and technicians, and its locomotive-like engines are powered by giant generators so large that they use the same technology as a diesel-electric locomotive. The force is distributed across 4 double-tracked belts, each containing 57 shoes and each shoe weighing over 2,000 pounds. It moves along a specially constructed crawlerway, a road made not of asphalt but of river rock, designed to bear the immense weight without crumbling. This painstakingly slow procession is a critical part of the ballet of spaceflight, a deliberate and powerful dance that underscores a simple truth. When you're moving the very tools of exploration, the future of a mission, there is no such thing as rushing. Every slow, deliberate turn of its massive treads is a statement of respect for the immense power and potential it carries towards the stars. After contemplating the immense, deliberate power required just to move a rocket to its launch pad, our perspective now expands from the terrestrial to the cosmic, to a scale so vast it defies human comprehension. We shift our gaze from the machines we build to the very fabric of the universe itself, where we've discovered structures of such mind-numbing proportions that they challenge the foundations of what we thought was possible. Imagine the largest thing you can: a mountain range, an ocean, our entire planet. Now push that thought further to our solar system, then the Milky Way galaxy, a glittering island of hundreds of billions of stars. That seems enormous enough, but our galaxy is just one member of a local group, which is itself a tiny part of the Virgo supercluster, a collection of thousands of galaxies spanning over 100 million light-years. And yet, in the grand cosmic scheme, even this supercluster is a mere speck, because in 2013, astronomers confirmed the existence of something that makes all of that look microscopic: the Hercules Corona Borealis Great Wall. This isn't a physical wall made of brick or stone, of course. It's a cosmic filament, an immense ribbon of galaxy clusters, dark matter, and gas, all woven together by gravity into the single largest known structure in the entire observable universe. Its scale is almost a form of violence against human intuition. This great wall stretches for over 10 billion light-years from end to end. To put that impossible number into some context, remember that a light-year is the distance light travels in 1 year, about 5.88 trillion miles. Now multiply that by 10 billion. This means that light, the fastest thing in existence, would take 10 billion years to travel from one end of this structure to the other. Considering the universe itself is only about 13.8 billion years old, this structure spans a significant fraction of all of time and space. Its discovery was a profound shock to cosmologists and immediately sparked a heated debate. The prevailing cosmological principle, a cornerstone of modern astronomy, suggests that when you look at the universe on a sufficiently large scale, matter should be distributed more or less evenly. It should appear smooth and homogeneous no matter where you look. The Hercules Corona Borealis Great Wall is a glaring contradiction to this principle. It is anything but smooth. It's a staggering concentration of matter, a colossal knot in the cosmic web so immense that its very existence forces us to question our models of how the universe evolved after the Big Bang. How could gravity have had enough time to pull together such an enormous structure so early in the universe's history? Its discovery tells us that our understanding of the cosmos, while advanced, is still in its infancy. We are still mapping the continents of reality, and we've just found a new one that is larger than any map we thought we could draw. To truly grasp its majesty, try this visualization. Picture our entire Milky Way galaxy as a single, standard-sized marble. On this scale, the distance to our nearest galactic neighbor, Andromeda, would be about another marble placed just a few feet away. The entire Virgo supercluster would then be a loose collection of these marbles scattered across a space roughly the size of a football field. Now, to model the Hercules Corona Borealis Great Wall, you would need to fill a container measuring over 6 miles wide, 6 miles long, and 6 miles tall with countless marbles, all interconnected in a specific web-like structure. Our entire local supercluster, that football field, would be just one tiny, insignificant cluster of marbles lost somewhere in the corner of this colossal container. It is a humbling reminder that for all our achievements, we inhabit an impossibly small corner of a stage whose true size we are only beginning to measure. While our bodies face strange new challenges in the void, they also undergo some truly bizarre and temporary transformations. Here's a fact that feels almost like a space-age superpower. The moment astronauts arrive in microgravity, they begin to grow taller. Imagine floating on board the International Space Station and realizing you're literally outgrowing your own body. This isn't an illusion. It's a direct and measurable physiological change caused by the absence of the one force that's shaped our entire existence, gravity. On Earth, gravity is a constant, compressive weight on our bodies, pressing down on us from the moment we stand up. Our spines, which are made up of 24 individual bones called vertebrae separated by soft, spongy discs, bear the brunt of this force. Throughout the day, this compression actually makes us slightly shorter. You might be a fraction of an inch taller first thing in the morning than you are by bedtime. In the microgravity environment of space, that constant downward pull simply vanishes. Without gravity to squeeze them together, the vertebrae in the spine are free to expand and relax. The cushioning discs between them, no longer compressed, absorb fluid and gently push each vertebra further apart. This process can add up to 3% to an astronaut's overall height. For an average person, that translates to a very noticeable gain of 1 to 2 inches, effectively making them taller than they've ever been in their adult lives. This sudden stretching, however, comes with a significant and often painful downside. The muscles and ligaments that are designed to support and stabilize the spine under Earth's gravity are suddenly forced to adapt to a completely new configuration. The body's entire support system is thrown into confusion, frequently leading to intense back pain and muscle stiffness, especially during the first few days of a mission. Many astronauts report a dull, persistent ache that makes it difficult to find a comfortable position, even in weightlessness. The body isn't just getting longer, it's being physically reshaped, and that process isn't always comfortable. The growth, while impressive, is only temporary. The moment an astronaut returns to Earth and gravity reasserts its pull, the process swiftly reverses. Over the course of a few hours or days, the spinal discs are compressed once more, and the astronaut gradually returns to their normal pre-flight height. This rapid return to normalcy underscores a fascinating truth about human physiology. We are profoundly and inseparably products of our planet. Our bodies are fine-tuned for a one-gravity environment, and when that constant is removed, even the most fundamental aspects of our architecture, like our height, can change in unexpected ways. It's a powerful, personal reminder that space isn't just a place we visit. It's an environment that actively and physically rewrites us from the inside out. That iconic image of the American flag, standing stiff and proud against the blackness of space, is seared into our collective memory. It's the ultimate symbol of a goal achieved, a moment of human triumph on another world. But if we could go back to those 6 Apollo landing sites today and look upon those flags with our own eyes, we would likely be met with a deeply different and strangely poetic sight. After more than 50 years of sitting in the most hostile museum imaginable, those flags have almost certainly been bleached bone white, their stars and stripes faded into nothingness. The violence of the lunar environment is difficult to overstate. Here on Earth, our atmosphere and magnetic field act as a protective shield, filtering out the sun's most harmful radiation and moderating temperature extremes. The moon has no such luxury. It is utterly exposed. The flags, made of ordinary nylon, were subjected to a constant, unrelenting barrage of unfiltered solar ultraviolet radiation. On Earth, UV radiation is what causes colors to fade in fabrics left out in the sun. It breaks down the chemical bonds in dyes. On the Moon, this process wouldn't be a slow fade over decades. It would have been devastatingly rapid. Scientists estimate that the intense UV bleaching effect would have stripped the flags of their iconic red, white, and blue in a matter of mere days, leaving behind nothing but blank white nylon. And if the radiation wasn't enough, the extreme temperature swings would have hammered the fabric relentlessly. A single lunar day lasts about 29 Earth days, meaning each flag endured over 2 weeks of continuous, blistering sunlight where surface temperatures soar to 253 degrees Fahrenheit, hot enough to boil water. This was immediately followed by an equally long night, where temperatures plunged to a soul-crushing negative 387 degrees Fahrenheit, colder than the surface of Pluto. This brutal cycle of baking and deep freezing, repeated over hundreds of times, would have made the nylon fabric incredibly brittle. It's likely that the flags are now riddled with microfractures, their material weakened to the point of disintegration. There is a poignant irony to this transformation. The most famous symbols of national achievement ever placed on another world have been systematically erased by the cosmos itself. They have been stripped of their national identity and returned to a blank, pristine state. They no longer represent one nation, they represent the human endeavor that got them there. They are a silent, universal monument to the act of exploration itself. While the flagpoles made of durable aluminum almost certainly still stand, casting long shadows across the gray dust, the blank white sheets fluttering atop them now tell a different story. They are a powerful reminder of the impermanence of our symbols in the face of the timeless, unforgiving nature of the universe. Our footprints may remain untouched for millions of years, but our flags could not withstand the sun. From the sterile, scent-controlled environment inside their spacecraft, astronauts stepping out for a spacewalk are greeted by the most profound silence imaginable. But when they return, they bring a ghost with them, a smell. After re-entering the airlock and removing their helmets, crews from the Space Shuttle and the International Space Station have consistently reported a strange, metallic odor clinging to their suits, their tools, and even their own skin. It's the lingering scent of the vacuum itself, and those who have experienced it struggle to find the perfect words, often landing on descriptions like seared steak, hot metal, welding fumes, or gunpowder. This presents a fascinating scientific puzzle because, of course, space is a near-perfect vacuum. You can't actually smell it while you're in it. Smell requires atmospheric particles to travel into our noses, and there are simply too few particles out there to breathe in. The scent isn't experienced until the astronauts are back inside, and their pressurized suits are introduced to the station's air. The prevailing theory points to a process happening right on the suit's exterior. The utter emptiness of space isn't truly empty. It's sprinkled with volatile compounds that can settle on surfaces. The most likely culprit is atomic oxygen, a highly reactive form of the element that doesn't exist naturally for long on Earth but is abundant in the high atmosphere, where solar ultraviolet radiation breaks apart normal oxygen molecules. As an astronaut works outside, these single oxygen atoms coat the surface of the suit. When the suit is brought back inside, this atomic oxygen interacts with the moisture and oxygen in the station's air, creating a very faint amount of ozone, that same clean, metallic smell you might detect after a lightning storm here on Earth. Another compelling theory suggests the scent could be originating from much further away. When massive stars die in violent supernova explosions, they forge and spew out complex molecules known as polycyclic aromatic hydrocarbons. These compounds are thought to drift throughout the cosmos, and it's possible that layers of this stardust, this essentially cosmic soot, slowly accumulate on the International Space Station and the suits. The moment they are brought inside and warmed, they could be off-gassing, releasing that smoky, metallic aroma that is, quite literally, the smell of dying stars. This strange sensory detail does more than just satisfy our curiosity. It transforms the abstract, intellectual concept of space into something tangibly real and physical. We can read data about plasma and vacuum pressures, but the idea that the universe has a scent, one that you can carry on your shoulder, makes it feel startlingly close. It connects the grand, impersonal cosmos directly to our most human of senses, reminding us that exploration isn't just about what we see through a viewport, but what we can, against all odds, experience for ourselves. It's almost a cosmic rule that the most astonishing discoveries are often found in the most violent and unlikely of places. While we might imagine planets forming in the serene disks around young, stable stars, the universe has a flair for the dramatic, creating worlds in the aftermath of stellar catastrophe. This brings us to a discovery that sounds less like astronomy and more like something from a science fiction heist movie, a planet made almost entirely of diamond. Officially catalogued as PSR J1719-1438b, this world orbits not a sun as we know it, but a rapidly spinning stellar corpse known as a pulsar. A pulsar is the incredibly dense, city-sized remnant of a massive star that went supernova. This particular pulsar spins over 10,000 times a minute, shooting out beams of radiation that sweep across space like a cosmic lighthouse. It was the mind-bending regularity of these pulses that allowed astronomers to detect the faint, gravitational tug of an orbiting planet in 2011. The planet's presence caused tiny, measurable variations in the timing of those pulses, revealing its existence. But what kind of planet could possibly survive the apocalyptic violence of a supernova and then orbit its terrifying remnant? The answer is as strange as it is dazzling. Scientists believe this planet, which is about 5 times the size of Earth but possesses a mass considerably greater, is the crystalline heart of a once mighty star. The leading theory suggests that this world began its life not as a rocky planet like Earth, but as a companion star, most likely a white dwarf. A white dwarf is the Earth-sized core of a star that has exhausted its fuel. It's incredibly dense, composed mostly of carbon and oxygen. When this system's more massive star reached the end of its life and exploded, the blast would have stripped away the outer layers of its white dwarf companion. What remained was the white dwarf's naked core, an object almost pure in carbon. Then, the immense gravitational pressure from the nearby pulsar went to work. Under such unimaginable force, pressures millions of times greater than what we experience on Earth, the carbon atoms were forced into a rigid, crystalline structure. In essence, the entire planet was subjected to a natural process of cosmic diamond making on a scale we can scarcely comprehend. The result is a planet that is likely one gigantic gem, a celestial diamond with a mass greater than that of Jupiter, yet compressed into a sphere not much larger than our own world. This glittering abomination of physics forces us to expand our definition of what a planet can be. It's a world without mountains, oceans, or an atmosphere, just a seemingly endless, flawless crystal lattice, forever trapped in the gravitational grip of its dead stellar partner. It's a place where the very ground beneath your feet, if you could stand on it, would be the hardest, most valuable material known to science. Of course, its practical value is zero. It exists 4,400 light-years away, and its extraction is a physical impossibility. But its symbolic value is infinite. PSR J1719-1438b is a stunning monument to the transformative power of the universe, proving that even in death and destruction, the cosmos can craft things of impossible beauty and wonder. It's a humbling thought that the universe's grandest secrets can sometimes be undone by an error almost too small to measure. This was the devastating reality for NASA in the spring of 1990, when the Hubble Space Telescope, the most complex and expensive observatory ever built at the time, opened its eye to the universe and saw only a blur. After decades of planning, a budget of $1.5 billion, and the triumphant launch aboard the Space Shuttle Discovery, the project was immediately plunged into a full-blown crisis. The first images it sent back were not the crystal-clear vistas of distant galaxies scientists had dreamed of. They were soft, fuzzy, and utterly useless for the cutting-edge science that had been promised. The problem wasn't that Hubble was broken, it was that it had been built with a profound and profoundly tiny flaw. The source of the nightmare was a calamity of precision. The telescope's primary mirror, a beautifully polished disc of glass over 7 feet across, was the wrong shape. But the error wasn't some massive manufacturing gash. It was a microscopic miscalculation known as a spherical aberration. The edge of the mirror had been ground too flat by a mere 2 micrometers. That's just 2/1,000,000ths of a meter, or about 1/50th the width of a single human hair. This unimaginably small error meant that light rays striking the edge of the mirror were being focused to a slightly different point than light rays striking the center. Instead of all the light from a distant star converging into a single, sharp point of focus, it was spreading out into a hazy circle, dooming the images. The flaw was so minute that the mirror was in fact one of the most perfectly shaped surfaces ever created by human hands. It was just perfectly wrong. The revelation triggered a media firestorm and deep congressional scrutiny. Hubble was instantly transformed from a symbol of American technological prowess into a national joke. A $1.5 billion blunder splashed across newspaper headlines and late-night television monologues. For the scientists and engineers who had dedicated their careers to the project, it was a period of profound despair. Yet within that crisis, a solution began to form. The very design that had become Hubble's greatest weakness, its location in orbit and its build for astronaut servicing, now became its greatest strength. If they couldn't bring the mirror back to Earth, they would have to bring the eye doctor to space. The fix was a masterpiece of optical engineering called COSTAR, the Corrective Optics Space Telescope Axial Replacement. It was essentially a set of 5 pairs of eyeglasses, a complex contraption of tiny, precisely shaped mirrors that would intercept the blurry light from the flawed primary mirror, correct its path, and bounce it sharply into the awaiting instruments. Installing it would be one of the most complex and ambitious spacewalks ever attempted. In December 1993, the crew of the Space Shuttle Endeavour embarked on a high-stakes orbital repair job, conducting a series of 5 grueling spacewalks over 11 days. With millions of people watching on live television, they successfully swapped out instruments and installed the COSTAR unit. The tension was unbearable until the moment the first corrected image was received. It was perfect. The universe snapped into a clarity never before seen. Distant stars were sharp pinpricks of light, and nebulas revealed structures hidden for all of human history. The story of Hubble's failure and recovery is one of the most powerful in the history of science. It's a testament to the fact that even our most ambitious endeavors are human and therefore fallible. But more importantly, it's a story of human ingenuity, perseverance, and the refusal to give up on a vision. That tiny flaw and the brilliant solution that overcame it didn't just save a telescope, it ultimately gave Hubble the legendary vision that would rewrite our textbooks and capture the awe of the entire world, proving that sometimes our greatest triumphs are born from our most humbling setbacks. If you think adjusting to a new time zone on Earth is disorienting, try wrapping your head around the clock on Venus. Here, the very definitions of a day and a year are turned completely upside down in one of the solar system's most bizarre orbital paradoxes. For us on Earth, the rhythm of life is simple. Our planet completes one full spin on its axis every 24 hours, giving us a day, and it makes one leisurely journey around the Sun every 365.25 days, giving us a year. On Venus, this logical order doesn't just break down, it shatters. A single day on Venus, the time it takes for the planet to make one complete rotation, lasts an agonizing 243 Earth days. To put that in perspective, from the moment the Sun rises over a point on Venus, you would wait over 8 months for it to rise again. But here's where the cosmic weirdness truly kicks in. In less time than that, just 225 Earth days, Venus has already finished a full lap around the Sun. This means a year on Venus is actually shorter than its day. You could celebrate your second birthday on Venus before you've even finished your first day. This extreme slow spin is compounded by another profound oddity. Venus rotates backwards. If you were to look down on the solar system from above the Sun's north pole, you'd see most planets, including Earth, spinning counter-clockwise on their axes as they orbit. Venus is the glaring exception, spinning clockwise in what astronomers call a retrograde rotation. This means on Venus, the Sun would appear to rise in the west and set in the east, a sight utterly alien to our experience. The question of how Venus ended up with this topsy-turvy, sluggish spin is one of planetary science's great puzzles. The leading theory points to a colossal gravitational tug of war in the planet's distant past. Some astrophysicists suggest that in the chaotic early solar system, the Sun's powerful tidal forces, combined with the gravitational pull of a thick, dense atmosphere, may have gradually slowed the planet's original spin to a crawl and eventually reversed it. Others propose a more catastrophic origin, a gigantic, glancing impact with another protoplanet early in its history, a collision so violent that it literally sent the world spinning the wrong way and drastically slowed its rotation, leaving it in its current peculiar state. Living on the surface of Venus would be a lesson in profound temporal confusion. The combination of its incredibly long day and its retrograde rotation creates a solar day, the time from one noon to the next. That is a completely different measurement altogether. Because the planet is slowly spinning backwards as it moves forward in its orbit, it takes Venus 117 Earth days to go from one sunrise to the next. So, while a sidereal day is 243 Earth days, the Sun only appears in the sky every 117. This means a Venusian year contains just about 1.92 Venusian solar days. You would experience nearly 2 full day-night cycles for every single trip around the Sun. This bizarre celestial mechanics transforms Venus from just another cloud-shrouded world into a profound example of how diverse planetary environments can be. It reminds us that the familiar rhythms of our own world are not a universal constant, but merely one possible outcome in a galaxy brimming with strange and wonderful possibilities. But for all its overwhelming power, the quasar's water cloud is simply too distant and too alien an environment to be a plausible candidate for life as we know it. The real excitement in the search for cosmic water lies much closer to home, right here in our own solar system, where 2 small, icy moons have completely rewritten the rules of where life could potentially thrive. The first is Saturn's brilliant white moon, Enceladus. From a distance, it appears as a frozen, airless ball of ice, a place where nothing could possibly be happening. That all changed in 2005 when the Cassini spacecraft witnessed one of the most stunning sights in the solar system. Enormous geysers of water vapor and ice crystals erupting from massive fissures near the moon's south pole, shooting hundreds of miles into space. Cassini didn't just observe these plumes from a distance, it flew right through them, and its onboard instruments made a breathtaking discovery. This wasn't just water. The plumes contained organic compounds, the basic chemical building blocks of life, and tiny grains of silica rock that can only form in liquid water that's in contact with a rocky seabed at temperatures of at least 90 degrees Celsius. The picture that emerged was undeniable. Enceladus harbors a vast, global saltwater ocean hidden beneath its icy crust, and this ocean is being heated and churned by the immense gravitational forces of Saturn, a process known as tidal heating. Even more astonishing, the chemistry of that water, with its salinity and alkaline pH, is strikingly similar to that of hydrothermal vents deep in Earth's oceans, places that are teeming with life completely independent of the Sun's energy. Enceladus isn't just a frozen rock, it's an active water world complete with energy sources, organic material, and liquid water, all the key ingredients for life. Not to be outdone, Jupiter's moon Europa presents an equally compelling, and perhaps even more expansive aquatic environment. Europa's surface is a cracked and jumbled landscape of ancient ice, crisscrossed with long, dark streaks that scientists believe are fractures where subsurface water has welled up and refrozen. The evidence for a Europan ocean is overwhelming. Measurements of the moon's magnetic field and its gravitational tug on passing spacecraft strongly suggest a global liquid water ocean, locked between a rocky mantle and an ice shell estimated to be 10 to 15 miles thick. The volume of water in this hidden sea is staggering. It's estimated to contain more than twice the amount of liquid water found in all of Earth's oceans combined. Like Enceladus, Europa is also kept warm and liquid by the relentless gravitational kneading from its giant parent planet, Jupiter. The implications of these discoveries are nothing short of revolutionary. We once believed that for a world to have liquid water and the potential for life, it had to orbit within a narrow, Goldilocks zone around its star, not too hot, not too cold. Yet here are two worlds far outside this traditional habitable zone, frozen solid on the surface but positively balmy and wet on the inside, powered not by sunlight but by the gravitational dynamics of their planetary systems. They have forced us to completely redefine the very concept of habitability. Life on Earth may have begun around sunlit shores, but it may thrive elsewhere in the total darkness of a subterranean sea, drawing energy from the heat and chemistry of rocks. This opens up an incredible array of new possibilities, suggesting that ocean worlds could be common throughout the galaxy, hidden beneath the icy surfaces of moons orbiting gas giants. The search for life is no longer confined to looking for Earth-like planets. It now includes sending probes to taste the geysers of Enceladus and eventually drill through the ice of Europa, seeking answers to the timeless question of whether we are alone in the universe. But that brilliant, life-giving beam of sunlight that warms your face on a summer afternoon, it's far, far older than the 8 minutes it spent racing across the void to reach you. In fact, the journey of a single photon of sunlight is an epic tale of persistence, a staggering multi-millennial struggle to escape the very star that created it. The light you see today began its incredible voyage during the peak of Earth's last ice age, when woolly mammoths still roamed the plains and early humans were painting on cave walls. To understand this, we need to follow the light back to its source, not to the sun's surface, but to its unimaginably dense and furious core. This is the stellar engine room, where temperatures soar to over 27 million degrees Fahrenheit and pressures are more than 250 billion times greater than the air pressure we feel at sea level. Here, in this extreme environment, hydrogen atoms are constantly being fused into helium in a monumental release of energy. This process creates photons of light, but their birthday in the core is just the beginning of an almost impossibly long and difficult journey. The second it is born, this new photon of light immediately slams into a wall of chaos. The sun's interior is not empty space. It's an incredibly dense soup of superheated plasma, a seething maelstrom of atomic nuclei and free electrons. For the photon, trying to travel straight out from the core is like trying to walk in a straight line through an impossibly crowded, chaotic pinball machine where the bumpers are themselves constantly moving. Instead of a clean, direct path to freedom, the photon embarks on what physicists call a random walk. It travels a minuscule distance, often less than a millimeter, before it is absorbed by a nearby atom. That atom, now energized, almost immediately spits out a new, identical photon in a completely random direction. This new photon then flies another tiny distance before the entire process repeats itself. Absorption, re-emission, over and over and over again, in a dizzying, zigzagging path with no clear direction. This process is so inefficient that if a photon could travel in a straight line from the core to the surface, the trip would take barely over 2 seconds. But because of this constant scattering and absorption, its actual path is a meandering, tortuous struggle. Scientists estimate that it can take a single photon anywhere from 10,000 to a staggering 30,000 years to finally fight its way to the Sun's surface, a journey of roughly 430,000 miles that has been stretched across eons. Once it finally reaches the surface and bursts free, that long-awaited moment of liberation, its final sprint to Earth across 93 million miles of empty space, is over in a mere 8 minutes and 20 seconds. The sunlight we depend on every day is an ancient traveler, a relic from a time when our world was a very different place, finally arriving to tell its story. It's a beautiful reminder that the universe operates on timescales that can dwarf human history, and that even the most constant features of our daily lives are embedded in a deep, wondrous, and ancient cosmic narrative. As we contemplate the sheer density of that distant water vapor and the ancient journey of sunlight, it's worth turning our attention to a much more tangible and frankly delightful property of the planets in our own neighborhood. We often think of the planets as immense, heavy spheres of rock and gas, but one of them defies that expectation in the most wonderfully counterintuitive way. If you could somehow find a celestial bathtub filled with enough water, the sixth planet from our Sun, the magnificent ringed world of Saturn, would not sink. It would bob gently on the surface like a colossal, striated beach ball. This isn't a trick of semantics or a playful exaggeration. It's a direct result of fundamental physics. The property at play here is density, which is essentially a measure of how much mass is packed into a given volume. Water is the universal comparison point, with a density of precisely 1 gram per cubic centimeter. Anything with a density lower than that will float, anything denser will sink. Saturn's average density has been calculated at a remarkably low 0.687 grams per cubic centimeter. This means that, on average, the entire planet is less dense than water. It is the only planet in our solar system that can claim this bizarre distinction. The reason for this astonishing lightness becomes clear when we remember what Saturn actually is. It's not a solid, rocky world like Earth or Mars. It's a gas giant, a behemoth composed predominantly of the 2 lightest elements in the universe, hydrogen and helium. Imagine the entire planet as a vast atmospheric ocean with no solid surface to speak of, just layers of gas that get progressively denser and hotter the deeper you go, eventually becoming a metallic, liquid form of hydrogen near the core. While Saturn has a rocky core, it is absolutely dwarfed by the immense volume of incredibly lightweight gas that surrounds it, pulling the planet's overall average density down to a fraction of our own world's. To truly grasp the scale of this thought experiment, you have to envision a bathtub of almost impossible proportions. Saturn has a diameter of over 72,000 miles. A container large enough to hold it would need to be unthinkably vast. Now picture this titanic sphere with its stunning, intricate system of rings spanning nearly twice its width, gently lowered into this cosmic ocean. It wouldn't plunge into the depths. Instead, it would settle with a significant portion of its bulk remaining above the surface, its iconic bands of tan and gold shimmering under the light of a distant sun. It's a surreal and almost humorous image, a testament to the fact that the universe often operates in ways that defy our everyday earth-bound logic. This single, simple fact about density does more than just amuse us. It provides a crucial insight into the very nature of the gas giants, reminding us that size alone does not dictate weight, and that even the grandest structures in the cosmos are governed by the same simple rules we learn in a school science lab. Yet for all the focus on preparing for the work of space, there's an equally important challenge that awaits every astronaut upon their return: the simple yet profound act of walking. Imagine stepping off a spacecraft after months of living in a floating environment, your legs feeling like foreign objects, your sense of balance completely scrambled. Your first few steps back on solid ground are often wobbly, uncertain, and require immense concentration. Many astronauts describe the sensation as feeling incredibly heavy, as if they are wearing a lead suit, and the act of simply standing upright without holding onto something for support is a genuine struggle. This period of readaptation, known as the deconditioning period, can last for days or even weeks as the body works to rebuild the muscle mass and bone density lost during the mission, and just as importantly, as the brain relearns how to interpret gravity's constant, unyielding pull. It's a humbling reminder that the human body is a product of its environment, and that the greatest exploration often brings us right back to the fundamental marvel of our own earth-bound existence. While our moon appears as a constant, silent companion in the night sky, its presence is anything but permanent. In a cosmic dance that began billions of years ago and will continue for billions more, the moon is in fact slowly leaving us. Thanks to the laser reflectors placed on the lunar surface by the Apollo astronauts, we can measure this retreat with astonishing precision. The moon is spiraling away from Earth at a rate of about 1.5 inches or 3.8 centimeters every single year. The engine behind this gradual departure is the same force that creates the ocean's tides, gravity. The moon's gravitational pull tugs on our planet, causing the oceans to bulge slightly towards it. Because Earth rotates on its axis much faster than the moon orbits around us, our planet's spin actually drags this watery bulge slightly ahead of the moon. This ahead-of-schedule tidal bulge then exerts its own gravitational pull on the moon, which has a curious effect. This constant, gentle tug acts like a microscopic gravitational slingshot, transferring a tiny amount of energy from Earth's rotation to the moon's orbit. This extra energy doesn't make the moon move faster. Instead, it pushes the moon into a slightly higher and therefore slower orbit. It's a perfectly balanced transaction. Earth loses a little bit of its rotational energy, causing our planet's spin to slow down and our days to get ever so slightly longer, and the moon uses that energy to inch further away. This process hasn't always happened at the same rate. Billions of years ago, when the moon was much closer, Earth spun much faster. A day may have been only 5 or 6 hours long. The tidal forces were immensely stronger, and the moon would have been receding at a much more rapid pace. As the distance has grown and Earth's spin has slowed, the whole process has decelerated to the leisurely pace we measure today. This dynamic relationship forces us to completely reframe our perception of the heavens. The solar system is not a static, unchanging clockwork. It is a living, evolving system where even the most fundamental relationships are in constant flux. Looking far into the future, this slow-motion escape has fascinating implications. In about 600 million years, the moon will have drifted so far away that it will no longer be able to completely cover the sun during a total solar eclipse. Those breathtaking moments of totality where day turns to night and the sun's corona shimmers in the sky will become a thing of the past, a memory from an earlier chapter in Earth's history. The moon will appear slightly smaller in the sky, and perfect alignment will be a thing of the past. While the moon's retreat is too slow to have any noticeable effect within a human lifetime, or even across all of human civilization, it is a powerful reminder that our place in the cosmos is part of a grand billion-year story that is still being written. While we often look up at the night sky and see a pristine, empty void, the reality is that the space just above our atmosphere has become the most exclusive and dangerous junkyard in the known universe. We've filled the orbital lanes with a swirling cloud of our own making, a halo of debris that now poses one of the most pressing and practical threats to our future in space. This isn't a few lost wrenches, it's an environmental crisis of cosmic proportions. Right now, there are over 500,000 pieces of debris the size of a marble or larger, and a staggering 100 million more fragments smaller than a centimeter, all trapped in orbit around our planet. To understand the danger, you have to forget everything you know about speed on Earth. Up there is no air resistance to slow things down. These objects are in a perpetual state of freefall, orbiting at velocities of around 17,500 miles per hour. At that speed, which is about 10 times faster than a bullet fired from a high-powered rifle, even a fleck of paint carries the destructive energy of a falling anvil. A single screw or a bolt becomes a hypervelocity projectile capable of puncturing the hull of a spacecraft or crippling a critical satellite. The International Space Station regularly performs debris avoidance maneuvers to steer clear of tracked objects, and its crew has to retreat into their soy as lifeboats when a piece of unknown debris passes too close, a sobering reminder that their home is constantly navigating a celestial minefield. The true nightmare scenario for orbital operations isn't just a single collision. It's a theoretical cascade of destruction known as the Kessler syndrome, named after the NASA scientist Donald J. Kessler, who first proposed it in 1978. The theory posits a terrifying domino effect. One collision between two objects creates thousands of new fragments. Each of those new pieces, now themselves traveling at astronomical speeds, significantly increases the probability of further collisions, which in turn create even more debris. This could trigger an unstoppable chain reaction, where the density of objects in low Earth orbit becomes so high that collisions become inevitable and frequent, effectively creating a self-sustaining shroud of shrapnel that could render entire orbital altitudes unusable for generations. It would be like wrapping our planet in a blanket of speeding bullets, making it too dangerous to launch new satellites or spacecraft without them being immediately punctured and destroyed, potentially locking us on Earth for centuries. This isn't just a scary story. We've already seen the opening act. In 2009, the theoretical became terrifyingly real. A defunct Russian communications satellite named Cosmos 2251, which had been dead in orbit for over a decade, slammed into an operational American commercial satellite, Iridium 33. The collision, occurring over 490 miles above Siberia, was catastrophic. The impact vaporized both spacecraft, instantly creating over 2,000 new, large pieces of trackable debris and countless smaller fragments, all added to the existing cloud. This single event increased the known debris population in low Earth orbit by a staggering 10% overnight. Each one of those new objects became a potential weapon, their orbits calculated and monitored by space agencies around the world, a permanent addition to the hazard map of space. The problem is compounded by historical practices. In the early days of the space race, little thought was given to cleanup. Spent rocket stages, dead satellites, and even the gloves lost by astronaut Ed White during the first American spacewalk were simply left where they floated. We treated space as an infinite dumping ground. The wake-up call has been loud and clear. Today, modern satellites are often designed with end-of-life plans, using their last reserves of fuel to either deorbit and burn up in the atmosphere or to move up to a less crowded graveyard orbit. But the existing debris remains a ticking clock. Solving this will require a new era of space ingenuity, from developing robotic garbage collectors and nets to even more advanced ideas like lasers to nudge smaller pieces out of the way. The silent, invisible traffic jam we've created above us is a stark lesson in responsibility, proving that our reach into the cosmos must be matched by a commitment to preserve it. But just as we grapple with the man-made chaos encircling our planet, astronomers are chasing a ghost at the very edge of our solar system, a specter of gravity whose presence is felt but never seen. The story of a hidden world orbiting in the deep freeze beyond Neptune is one of the most captivating detective stories in modern astronomy, a tale that feels strangely familiar. It seems we might be on the verge of finding a ninth planet all over again. The search for this world, unofficially dubbed Planet 9, began not with a glimpse through a telescope but with a pattern on a page. Astronomers studying the orbits of small, icy bodies in the distant Kuiper belt, a region far beyond Neptune filled with frozen leftovers from the solar system's formation, noticed something profoundly strange. The most distant of these objects, known as extreme trans-Neptunian objects, didn't have randomly oriented orbits as one would expect. Instead, their elongated paths around the Sun were mysteriously clustered, as if an invisible shepherd were herding them, guiding their journeys with an immense gravitational hand. The odds of this clustering happening by pure chance are astronomically low, calculated to be somewhere around 0.0007%. This compelling gravitational evidence points to one compelling explanation: a previously undetected planet with a mass estimated to be 5 to 10 times that of Earth, lurking in the perpetual twilight of the outer solar system. Its proposed orbit is almost unimaginably vast and slow. This world would swing along an elliptical path that brings it no closer than about 200 astronomical units from the Sun. That's 200 times the distance from the Earth to the Sun, and could take it as far out as 1,200 astronomical units. A single year on this hypothetical planet, one complete trip around the Sun, could take between 10 and 20,000 Earth years. To put that in perspective, the last time it was in the position it is today, human civilization was in its infancy. What would this world be like? Theorists suggest it's most likely a super-Earth or a mini-Neptune, a rocky planet with a thick atmosphere, or perhaps an icy giant with a solid core. It would be a frozen, dark world, so far from the Sun that our star would appear as little more than an exceptionally bright pinprick in a black sky, offering no warmth or light. The hunt for this phantom is now in full swing, utilizing some of the most powerful telescopes on Earth, like the Subaru telescope in Hawaii and the Vera C. Rubin Observatory, currently under construction in Chile. These instruments are meticulously scanning the vast proposed orbital path, looking for the faint, slow-moving dot of light that would confirm its existence. It's a painstaking process, like searching for a single specific grain of black sand on a dark beach at night. This search for Planet 9 is a beautiful echo of history, a direct parallel to the 19th century discovery of Neptune itself, which was found not by accident but because its gravity was subtly tugging on the orbit of Uranus. We are once again using the language of mathematics and the subtle irregularities in the motion of distant objects to predict the existence of a world we cannot yet see. It's a powerful testament to the predictive power of physics. Whether Planet 9 is ultimately found or whether the strange orbital clues are explained by some other, even more exotic phenomenon, the search itself is revolutionizing our understanding of the dynamic and still mysterious outer reaches of our own celestial neighborhood. While the search for a distant, unseen planet captivates astronomers, some of the most perplexing stories in space exploration come not from cold data, but from first-hand human experience. In 1981, aboard the Soviet space station Salyut-6, cosmonaut Vladimir Kovalyonok witnessed something that defied easy explanation. He reported seeing a small, glowing object outside the station that suddenly and violently exploded into multiple pieces. But the most enduring and bizarre account from the Soviet program occurred years earlier in 1991, when the crew of Salyut-7 encountered something far stranger. According to their reports, the station was approached not by a single object, but by a formation of 5 luminous, silent beings. The cosmonauts described them as angelic figures, humanoid in shape and radiating a brilliant, blinding light, their forms seeming to keep perfect pace with the station for several minutes before vanishing as mysteriously as they had appeared. This incredible story, recounted by seasoned, trained professionals, is a staple of space mystery lore. It's a narrative that immediately ignites our imagination and begs the question of what they truly saw out there. The human desire to believe in the extraordinary is powerful, and the idea of a celestial visitation is undeniably alluring. However, the most likely explanations for this event are rooted not in the supernatural, but in the profound and often bizarre physical and psychological realities of spaceflight. One of the most plausible theories points to a phenomenon as simple as it is beautiful: space dust. The station is constantly surrounded by a fine mist of particulate matter, tiny fragments from micrometeorites or even its own waste venting. When the station passes into direct sunlight from the darkness of Earth's shadow, these particles can suddenly be illuminated with spectacular intensity. If this cloud of dust was vented in a specific, controlled manner, say, from a thruster firing, it could easily coalesce into distinct, shimmering shapes that appear to move in formation with the station, creating the illusion of intelligent accompaniment. Another strong contender is the effect of extreme environmental stress on the human mind. The cosmonauts were living in a high-pressure, isolated, and dangerous environment. The constant hum of machinery, the perpetual freefall, and the sheer cognitive load can induce unique neurological effects. It's well documented that sensory deprivation and intense psychological strain can lead to vivid hallucinations. The brain, desperate for familiar stimuli, might project recognizable patterns like humanoid figures onto random light patterns or reflections on the station's own windows. This wouldn't be a sign of weakness or instability, but rather a testament to the incredible strain we place on our own biology when we venture into the void. A third, more technical possibility involves the station's own systems. The complex machinery of a space station regularly vents gases and fuel, which can instantly freeze into expansive, glittering clouds of ice crystals in the vacuum. If a series of small attitude control thrusters fired in sequence, each puff of propellant could create a temporary glowing plume. From the right viewing angle inside the station, these plumes could align in a way that, to the human eye, resembles a procession of distinct, organized entities moving in unison. The radiant appearance could simply be sunlight catching these crystal clouds at the perfect angle, transforming a routine mechanical process into a moment of breathtaking and deeply confusing spectacle. The enduring power of the Salyut 7 story isn't necessarily about proving or disproving extraterrestrial life. Instead, it serves as a fascinating case study in the intersection of human perception and the utterly alien environment of space. It reminds us that the cosmos is filled with phenomena that can challenge our senses and our sanity. These accounts, whether ultimately explained by ice crystals or psychology, are a crucial part of the history of exploration. They represent the moments where our brave pioneers ventured into the unknown and encountered something for which their extensive training simply could not prepare them. They highlight that the final frontier is not just a physical space to be mapped, but a psychological and perceptual landscape where the lines between reality and illusion can become wonderfully and terrifyingly blurred. While our planet sports impressive peaks that scrape the sky, Earth's volcanic achievements are utterly dwarfed by a titan waiting next door. On the rust-colored plains of Mars stands a mountain so colossal it redefines the very scale of planetary geology. This is Olympus Mons, the largest volcano in the entire solar system, a breathtaking monolith that makes our greatest mountains look like mere foothills. To truly grasp its size, imagine an entire United States national park, but one built on a planetary scale. Olympus Mons is so wide that its base would completely engulf the entire state of Arizona. Its height is even more staggering, soaring 16 miles into the thin Martian sky. Picture stacking 3 Mount Everests, one on top of the other, and you still wouldn't reach the summit of this volcanic behemoth. If you stood on its peak, the slope would curve away over the horizon, and the caldera, the volcanic crater at the top, is so vast you could fit the entire island of Oahu inside it. This unbelievable scale isn't just a random occurrence, it's a direct result of a fundamental difference between Mars and Earth. Our planet is a dynamic, shifting jigsaw puzzle of tectonic plates that constantly slide, collide, and recycle the crust. This movement means that a volcanic hotspot, like the one fueling the Hawaiian Islands, doesn't get to build a single, enormous volcano forever. As the Pacific Plate slowly drifts over the stationary magma plume, the hotspot punches through the crust to create a new volcano, leaving the old one to go extinct. This creates a chain of islands, each one a separate monument to the hotspot's power over millions of years. Mars, however, chose a different geological path. Billions of years ago, the red planet lost its internal heat much faster than Earth, causing its tectonic activity to grind to a halt. The Martian crust became a single, stationary, planetary-wide plate. Without the shuffling motion of tectonics, a volcanic hotspot on Mars was given a geological gift: permanence. For possibly 2 or 3 billion years, a single, incredibly stable and long-lived magma chamber kept erupting in the same exact spot. Layer upon layer of lava flows steadily accumulating into a single, gargantuan structure. There was no crustal movement to carry it away, no competing volcanoes to siphon its magma. It was free to grow, uninterrupted for eons, resulting in the incredible shield volcano we see today. Its slopes are remarkably gentle, typically only a 5% grade, because the low-viscosity lava that built it was able to flow for incredible distances before cooling and solidifying, creating a mountain that is less about steep, dramatic cliffs and more about unimaginable, sprawling bulk. Olympus Mons is more than just a record holder. It's a frozen monument to the geological history of its world. It tells a story of a planet that started with fiery volcanic fury, but has since settled into a deep, cold quiet. It stands as a silent guardian over a largely dead world, a relic from a time when Mars was a much more active and potentially Earth-like place. Its immense presence challenges our perceptions of what is possible, offering a humbling perspective on the forces that shape planets and reminding us that elsewhere in the cosmos, the landscape operates on a scale we are only beginning to comprehend. And now, we turn our gaze to perhaps the most iconic photograph ever taken by the Hubble Space Telescope, the breathtaking Pillars of Creation. This stunning image, captured in 1995, reveals 3 towering tendrils of cosmic dust and gas standing like majestic, elephantine trunks in the heart of the Eagle Nebula. They are a stellar nursery of unimaginable scale, with the tallest pillar stretching an incredible 4 light-years from base to tip. For decades, this portrait has been a symbol of the universe's creative power, a place where new stars are constantly being forged from the raw material of the cosmos. But this beautiful picture holds a secret, a truth about time and light that is both heartbreaking and profoundly beautiful. The reality is, we might be looking at a cosmic ghost. The key to this celestial mystery lies in a simple but mind-bending number: 7,000. The Eagle Nebula is located roughly 7,000 light-years away from Earth. This means the light captured by Hubble's lens, the very photons that traveled across the void to create that image, began their journey 7,000 years ago. We are not seeing the pillars of creation as they are today. We are seeing them as they were when humanity's earliest civilizations were first developing writing and building the world's first cities. The image is a postcard from a distant past, a glimpse into a chapter of the nebula's history that concluded millennia before the pyramids were even a blueprint in the sand. This delay in cosmic information becomes even more intriguing when we consider what might have happened in the time since that light left the nebula. In 2007, astronomers using the Spitzer Space Telescope, which observes the universe in infrared light, detected something ominous. Their data suggested that the area around the pillars was being heated by a powerful shockwave. The most likely explanation is that a nearby massive star, having exhausted its fuel, ended its life in a cataclysmic supernova explosion. The theory posits that the blast wave from this stellar death would have raced outward at a significant fraction of the speed of light, and about 6,000 years ago, just 1,000 years after the light we now see left the pillars, this wave of pure, destructive energy would have slammed into those delicate structures. If this hypothesis is correct, the result would not have been subtle. The immense force and heat of the shockwave would have acted like a cosmic tsunami, violently compressing and then utterly obliterating the pillars. The delicate balance of forces that held the structures together would have been annihilated in an instant of cosmic time. The dust and gas would have been scoured away, and the stellar nursery would have been torn apart, its nascent stars sent spinning into the void. The pillars of creation, in their iconic form, would have been vaporized, yet here on Earth we continue to receive the old light. The photons carrying the news of this destruction are still traveling toward us, trapped in a slower, more tragic race. We are, in a very real sense, watching a memory of something that may no longer exist. The light showing their intact beauty is still arriving, while the light showing their demise is en route. This creates a bizarre and poignant period of astronomical limbo. We are observing an object that, for all we know, has already met its end. We won't know the final fate of the pillars for certain until the light from that hypothetical event finally reaches our telescopes, which won't happen for another 1,000 years. We are left with a profound lesson in the nature of observation. Astronomy is not a live broadcast of the universe, it is an archaeological dig through time. Every time we point a telescope at the heavens, we are peering into the past, and the further out we look, the deeper into history we see. The story of the pillars of creation is a powerful reminder of our place in the cosmos, not as passive viewers of a static stage, but as time travelers, forever sifting through the ancient light of events long since past, forever chasing echoes in the dark. Yet for all its immense power, your smartphone relies on a global network of cell towers, satellites, and power grids to function. The Apollo Guidance Computer, or a GC, had to work perfectly while hurtling through the void entirely on its own. Its processing speed was a mere 0.043 MHz. To put that into perspective, a common modern-day calculator has more raw computational power. The memory system was even more astonishing. Programmers didn't use silicon chips, they used something called rope core memory. This was a physical, hand-woven system where tiny magnetic rings or cores were threaded with wires by skilled technicians, often recruited from textile factories. If a wire passed through the center of a core, it represented a binary one. If it went around the outside, it was a 0. This meant the software was literally sewn into the hardware. Changing a single line of code wasn't a simple software patch. It required unthreading and reweaving this intricate digital tapestry by hand. This stark technological disparity forces a profound shift in perspective. We often marvel at the power of our modern devices, but the real wonder lies in what was accomplished with so very little. The GC's limited resources were not a drawback but a design feature. In the critical moments of a lunar landing, there was no room for a system crash or a software glitch. The computer had to be ruthlessly reliable. Its slow, deliberate processing and its physically woven memory were incredibly robust, immune to the radiation and extreme temperatures of space in a way that modern, delicate microchips are not. Every cycle of processing power was dedicated to a single, vital purpose: getting astronauts to the moon and back safely. It wasn't built to multitask or run apps, it was built to navigate, and it did that one job with flawless perfection. This comparison isn't about dismissing the marvels of modern technology, but about reframing our definition of power. Computational brute force is one thing, but the true measure of achievement is what you accomplish with the tools you have. The engineers and programmers of the Apollo era were masters of efficiency, squeezing every last bit of potential from a machine that by today's standards seems impossibly primitive. They demonstrated that ingenuity, creativity, and meticulous problem-solving can achieve the impossible, even without billions of transistors at your disposal. Your phone may be a universe of information in your pocket, but it stands on the shoulders of a tiny, woven giant that first showed us how to reach for the stars. But as we marvel at the longevity of a mission like Voyager, sailing smoothly into the void on a carefully plotted course. We must also acknowledge the stories of those that never made it, the lost spacecraft that haunt the orbital graveyards. And in that vast boneyard, there is one story that stands out not for its success, but for its eerie, inexplicable persistence. This is the tale of a zombie satellite, a ghost from the dawn of the space age that refused to be forgotten. In the mid-1960s, as the space race was hitting its stride, MIT's Lincoln Laboratory was developing a series of pioneering satellites known as the Lincoln Experimental Satellites. Their goal was to test and develop new technologies for military communications. In February 1965, LES-1 was launched atop a Titan III rocket, destined for a circular orbit 2,800 kilometers above the Earth. But almost immediately, something went terribly wrong. A failure in the spacecraft stabilization system prevented it from reaching its intended orbit. Instead of settling into a stable path, it was flung into a lopsided, elliptical orbit that sent it tumbling end over end, completely out of control. After a brief period of transmitting unintelligible data, it fell silent. The mission was declared a total loss, and the satellite was catalogued as just another piece of space junk, a forgotten relic from a bygone era. For 48 years, LES-1 was just an anonymous line in a debris tracking catalog, a piece of inert metal silently tumbling through the darkness. Its story should have ended there, but in 2013, an amateur radio astronomer and satellite tracker in the United Kingdom named Phil Williams made an astounding discovery. While scanning the skies with his home-built equipment, he stumbled upon a faint, rhythmic signal pulsing at a frequency of 237 MHz. The signal was weak and distorted, but it was unmistakably artificial. When he decoded its identity, he was stunned. The ghost calling out from the void was LES-1. The question, of course, was how. How could a spacecraft declared dead in 1965 possibly be transmitting nearly half a century later? The answer lies in a perfect, if spooky, storm of orbital mechanics and simple electronics. LES-1's chaotic, tumbling motion is the key. As it cartwheels through space, its body slowly rotates, bringing its 4 solar panels in and out of direct sunlight. For most of its orbit, it is in darkness, its systems dormant and frozen in the deep cold of space. But during the brief moments of its rotation, when the sun strikes the panels at just the right angle, they suddenly spring to life. Even after 5 decades, the robust photovoltaic cells are still capable of generating a tiny trickle of electricity, just enough to power up the old-fashioned, hardy vacuum tubes in its transmitter for a few precious seconds. This sudden jolt of power brings the dead back to life. The transmitter boots up and begins to broadcast its signal, the same signal it was programmed to send all those years ago. But then, as the satellite continues its tumble, the solar panels rotate back out of the sun, the power instantly cuts out, and the transmitter dies again mid-beep. The result is the ghostly signal that Phil Williams heard, a wavering, ethereal tone that sounds less like a machine and more like a theremin from an old horror movie, a mournful whoop-whoop-whoop that fades in and out as the satellite spins. It is the sound of a machine caught in an endless cycle of death and rebirth, a cosmic beacon from a time when astronauts were still preparing to walk on the moon. The persistence of LES-1 is more than just a curious anomaly. It's a profound testament to the durability of that era's engineering. Built without modern microchips, using robust components designed to withstand the unknown rigors of space, it has proven to be almost indestructible. It also serves as a poignant, if unintended, monument. Every time its signal whispers back to Earth, it is a voice from a generation of engineers and scientists who dared to imagine what was possible. They may be gone, but their creation, their electrical ghost, lives on, tumbling through the silent expanse, forever singing its simple, haunting song. Yet for all the symbolic power of a zombie satellite's lonely song, its value pales in comparison to the most ambitious structure humanity has ever placed in the heavens, a project whose price tag is as staggering as its engineering. Consider for a moment the most expensive things we build on Earth: sprawling nuclear aircraft carriers, vast interconnected highway systems, or shimmering new cities rising from the desert. Now, multiply that ambition by 15 nations and launch it into the most hostile environment imaginable. The International Space Station isn't just a scientific outpost. It is, by a colossal margin, the single most expensive object ever constructed by human hands, with estimated costs soaring well over $150 billion. To grasp what that number truly means, it helps to break it down. That sum could fund the entire Apollo program to the moon several times over. It could buy every professional sports franchise in the United States and still have tens of billions left for new stadiums. But this isn't money spent on luxury or entertainment. It is an investment in a permanent foothold for our species off our planet. For that price, we purchased a miracle of international logistics and engineering, a spacecraft the size of a football field, complete with its own wings of solar panels, hurtling around the Earth at 17,500 miles per hour. It is a home, a power plant, a laboratory, and a life support system all in one. Every single system aboard is a testament to that cost. The station's environmental control and life support system is a technological marvel that would have been pure science fiction just decades ago. It doesn't just store water and oxygen, it meticulously recycles them. The humidity from the crew's breath, their sweat, and even their urine is captured, purified, and transformed back into clean drinking water. The very air is scrubbed of carbon dioxide, which is then processed to recover oxygen. This closed-loop system is absolutely critical for long-duration missions, drastically reducing the need for constant, astronomically expensive resupply launches from Earth. It is a working prototype for how we might live on the Moon or Mars, turning waste back into life. The station itself is a patchwork of modules and components built by nations that were once fierce adversaries, now locked in an orbital handshake. The United States and Russia provided the core modules, while Japan's Kibo laboratory and Europe's Columbus lab add specialized research capabilities. Canada's contribution, the Canadarm2, is a sophisticated robotic arm that acts as a construction crane and a helping hand for capturing visiting cargo spacecraft. This wasn't a project any one nation could have shouldered alone, both financially and diplomatically. The constant flow of astronauts and cosmonauts, of Progress and Dragon and Cygnus spacecraft, represents a continuous 20-year-plus operation of supply, maintenance, and crew rotation, a dizzying ballet of launches and dockings that keeps the lights on and the science flowing. And what does all that money and effort ultimately buy? Beyond the symbol of cooperation, it purchases an unparalleled view into the universe and ourselves. The station's microgravity laboratory has hosted experiments in fluid physics, material science, and combustion that are impossible to perform on Earth, leading to advances in medicine, technology, and our understanding of fundamental physical processes. Most importantly, it has served as a long-duration testbed for the human body itself, providing invaluable data on muscle atrophy, bone density loss, and the effects of radiation, the very knowledge we need to survive the longer journeys to come. The International Space Station is far more than its price tag. It is a down payment on our future as a spacefaring civilization, a bold declaration that our greatest ambitions are worth the combined treasure and effort of our entire planet. Floating serenely in the constellation of Aquila, some 26,000 light-years from Earth, there is a cloud that could supply every party in the galaxy. This is Sagittarius B2, a vast molecular cloud near the center of our Milky Way, and within its swirling cosmic depths, astronomers have discovered a staggering reservoir of ethyl alcohol, the exact same kind of alcohol found in every beer, glass of wine, and spirit here on Earth. The sheer volume is almost impossible to comprehend. Scientists estimate this interstellar tavern holds enough booze to fill 400 septillion pints. To put that number in perspective, a septillion is a 1 followed by 24 zeros. If you could somehow distribute this celestial brew to every single person on Earth, each man, woman, and child would receive roughly 50 trillion pints. You could pour a pint for every person every single day for the next 30 million years, and you still wouldn't run out. Of course, actually trying to drink a pint of this space beer would be a uniquely terrible idea. Sagittarius B2 isn't a floating lagoon of ready-to-serve lager. It's an incredibly cold, diffuse cloud of gas and dust where complex molecules form on the surface of microscopic frozen grains. The alcohol is not sloshing around in a liquid form but exists as a vapor, spread so thin that if you were to fly a spaceship through it, you'd be highly unlikely to ever encounter a single molecule. The cloud is also laced with other, far less palatable chemicals, including formaldehyde, hydrogen cyanide, and a variety of other organic compounds that would make for a decidedly lethal cocktail. The real wonder of this discovery isn't the potential for a cosmic hangover, but what it tells us about the incredible chemical complexity of our universe. Sagittarius B2 is more than just a cloud of alcohol. It's a gigantic natural laboratory for prebiotic chemistry. Alongside the ethyl alcohol, astronomers have also detected vinyl alcohol, which is a direct precursor to more complex organic molecules. These aren't just random substances, they are the fundamental building blocks for amino acids and sugars, the very ingredients necessary for life as we know it. This suggests that the processes which eventually led to our own existence didn't begin on a young Earth, but were set in motion billions of years earlier in the cold, dark nurseries between the stars. The complex molecules that form on these dusty ice grains are then incorporated into new solar systems as the cloud collapses to form stars and planets. When a comet or asteroid from the outer reaches of a new solar system eventually crashes into a young, watery world like early Earth, it delivers a payload of these prebiotic ingredients, effectively seeding the planet with the raw materials for life. This changes our perspective on our own origins in a profound way. We are not just creatures of Earth, but children of the cosmos. The elements that make up our bodies were forged in the hearts of long-dead stars, and now we see that the very chemical pathways towards life itself may have begun in the immense cold clouds that drift between those stars. The universe, it seems, isn't just hospitable to life by chance. It appears to be actively and rather cheerfully building the ingredients everywhere we look. That cloud of alcohol isn't just a fun fact, it's a profound clue, a signpost pointing towards a universe that is inherently, chemically, primed for the possibility of life. Her story begins not with the careful selection of a purebred from a kennel, but on the harsh, cold streets of Moscow. Leica was a stray, a mixed-breed terrier perhaps 3 years old, scooped up by Soviet scientists for the fledgling space program. Strays were chosen for their perceived toughness and resilience, already hardened to survive in difficult conditions. She wasn't the only candidate. The program had several dogs, all females, for the practical reason that their space suits allowed for a simpler waste collection system. Leica's original name was Kudryavka, or Little Curly, but she would become known to the world by the simpler, more poignant name Leica, which simply means barker. Along with her companions, she was subjected to a brutal training regimen designed to simulate the terrifying experience of spaceflight. She was confined in progressively smaller cages for up to 20 days at a time to acclimate her to the extreme claustrophobia of the tiny capsule. She was spun in centrifuges to simulate the high G-forces of launch and placed in machines that vibrated violently to mimic the shuddering rocket. Through it all, her calm demeanor and survival instinct shone through, and she was chosen for the one-way mission, a decision made at the highest levels of the Soviet government for a propaganda triumph. On November 3, 1957, Just a month after the USSR had stunned the world with the launch of the first artificial satellite, Sputnik 1, Laika was sealed inside her tiny, pressurized cabin aboard Sputnik 2. The capsule was fitted with an oxygen generator, a device to absorb carbon dioxide, and just enough food in a gelatinized form for a several-day mission. Sensors were attached to monitor her heartbeat, blood pressure, and breathing. There was a window and a camera was trained on her face. As the R-7 rocket thundered to life, the data streamed back to anxious scientists on the ground showed her pulse triple from its resting rate, a sure sign of the immense stress and terror she must have been experiencing. But she survived the launch, and as the rocket's final stage cut off and silence descended, she became weightless. The data showed her heart rate gradually slowing, a sign that she was, against all odds, adapting. For a few hours, Laika was alive in orbit, the first living being from Earth to ever see our planet from such a vantage point, a lonely pioneer in the absolute black. The official Soviet narrative, carefully managed for decades, was that Laika lived for several days in orbit, was fed her final meal painlessly, and then was euthanized before her oxygen supply could run out. The world was told she had died peacefully. The truth, however, was far more tragic and was only revealed decades later. The technology for a safe re-entry had not yet been developed. Her death was a foreknown and accepted part of the mission from the very beginning. The cabin's life support system was only ever designed to last a short time. The real cause of her death, confessed by scientist Dmitry Malyshenkov in 2002, was a catastrophic failure of the thermal control system just a few hours into the flight. As the satellite passed in and out of sunlight, the capsule began to rapidly overheat. The primitive temperature regulation system was completely overwhelmed. The data showed her pulse rate rising again, this time not from stress but from the sheer, unbearable heat. Within 5 to 7 hours of achieving orbit, the temperature inside her tiny metal coffin soared to over 100 degrees Fahrenheit. Laika did not die peacefully in her sleep. She succumbed to heat stroke and panic, a terrible, lonely end for a creature who had only ever known the struggle for survival. The legacy of her sacrifice is profound and complex. At the time, her story was a monumental propaganda coup for the Soviet Union, demonstrating a clear lead in the space race and proving that a living organism could not only survive the violent launch into space but could also, at least for a time, function in the weightless environment. The biological data telemetered back, though cut short, was invaluable, giving scientists their first ever look at the physiological effects of spaceflight on a mammal. It paved the way directly for the subsequent missions that would carry and return dogs like Belka and Strelka alive, and ultimately for Yuri Gagarin's historic first human orbit. Yet her death also sparked the first major international debate on the ethics of animal testing in space exploration. Outrage was particularly fierce in the West, where animal welfare organizations and a concerned public protested what they saw as a cruel and unnecessary sacrifice. In the UK, the National Canine Defence League even called for a daily minute of silence for dog owners. This public pressure would eventually lead to the development of stricter guidelines for the humane treatment of animal test subjects in both the Soviet and American space programs. Today, Laika is remembered not just as a tool of Cold War politics, but as a poignant and unwilling hero. She was a small, powerless creature thrust into the center of a colossal human ambition. Monuments to her stand in Russia, and her image is forever stamped on the cultural memory of the world. Her story forces us to confront the difficult and often uncomfortable costs of progress, the moral price we are sometimes willing to pay for a leap into the unknown. She represents the very first, most vulnerable link in the chain of life that now extends to the International Space Station and beyond. A silent testament to the fact that every giant leap for mankind often begins on the small, trusting paws of a pioneer. After contemplating the small, brave dog who ventured into the void and the vast cloud of alcohol that drifts between the stars, we arrive at a truth that is perhaps the most profound of all. It is a concept that ties every single one of these weird and wonderful facts together, a thread that connects the grandest cosmic events to the most intimate parts of our own being. The final fact is this: you, me, everyone you have ever known or loved, and every living thing on this planet are all made of stardust. This is not a metaphor or a poetic flourish. It is the literal scientific story of our origin. To understand how this is possible, we have to rewind the clock of the universe almost 14 billion years to the moment of the Big Bang. In that initial, unimaginable fireball, the only elements that were created were the two very lightest, hydrogen and helium. For a long time, that was all the universe contained: a vast, expanding cloud of simple, primordial gas. There was no carbon for life, no oxygen for water, no iron for blood, no calcium for bones. The universe was fundamentally incapable of creating a planet, an ocean, or a person. The story of how we got from that simple beginning to the breathtaking complexity of today is written in the life and death of stars. A star is a cosmic alchemist, a giant fusion reactor that spends its life performing a miraculous transformation. In the crushing pressure and intense heat of a star's core, atoms of hydrogen are slammed together with such force that they fuse, creating helium and releasing enormous amounts of energy in the process. This is what makes a star shine. In stars much more massive than our Sun, this alchemy doesn't stop there. As the star ages, it begins to fuse helium into carbon, carbon into oxygen, and so on, climbing the periodic table step by step, all the way up to iron. For its entire life, a star is fighting a battle against the immense force of its own gravity, using the energy from these fusion reactions to hold itself up. But once its core becomes iron, the fusion process hits a wall. Fusing iron doesn't release energy, it consumes it. The star's internal support system suddenly vanishes. The result is a cataclysm of almost unbelievable violence, a supernova explosion. In less than a second, the star's core collapses and then rebounds in a shockwave that blasts the entire outer layers of the star out into the void at nearly the speed of light. The energy released in this final, defiant act is so immense that it forges all the elements heavier than iron: the gold in your jewelry, the silver in a photographic film, the uranium in a power plant, the iodine in your thyroid. Everything else is cooked in the unimaginable heat of the explosion itself. In its death throes, the star completes its ultimate purpose. It seeds the surrounding cosmos with a rich, new cloud of complex, heavy elements, the raw ingredients for everything that will come next. This process has been repeating for billions of years. Those enriched clouds of gas and dust, scattered by supernova and stellar winds, eventually collapse under their own gravity to form a new generation of stars. But now, these new stars are born with a legacy. They are surrounded by swirling disks of that same dust containing all those new, heavier elements. Within these disks, particles begin to stick together, forming rocks, then asteroids, then planets. Our own solar system formed from such a cloud, one that was laced with the remnants of countless ancient stars that lived and died long before our Sun was even a glimmer in a nebula. This means that every atom in your body that is not hydrogen, which is a relic from the Big Bang itself, was forged in the heart of a long-dead star. The oxygen you breathe right now was once fused in a star larger than our Sun. The carbon that forms the backbone of your DNA was created in the inner layers of a red giant. The iron that carries oxygen in your blood was synthesized in the final moments before a supernova. The calcium in your bones, the phosphorus in your ATP, the nitrogen in your muscles, all of it was once stardust, scattered across the light years and eventually drawn together by gravity to become part of our planet and ultimately part of us. This knowledge changes everything. It redefines our place in the universe. We are not just living on a planet orbiting a star. We are literally a way for the cosmos to know itself. We are the universe become conscious, a collection of atoms that has temporarily arranged itself into a form that can look back at the night sky, trace the history of its own components, and feel a sense of awe. The same forces of gravity and physics that govern the spin of galaxies and the explosion of stars are the very same forces that hold you to the Earth and power your thoughts. You carry the legacy of those ancient stars within you. Every time you feel insignificant under the vast night sky, remember this: you are not just a passive observer looking out at the universe. You are the universe looking back at itself. You are stardust, awake and wondering. And so our journey through the cosmos comes to a close, from the deceptively simple taste of astronaut ice cream that never was, to the profound realization that we are all, each and every one of us, made of recycled stardust. We've walked across the dusty, gunpowder-scented plains of the moon, stood in awe before the silent, wind-bleached flags that mark our first steps on another world, and we've ventured into the deep freeze of the outer solar system, where a planet of pure diamond orbits the corpse of a star. We've grappled with the mind-bending scale of cosmic structures so vast they defy the rules of physics, and we've felt the intimate human struggle of an astronaut unable to shed a tear in the weightless void. Space exploration, as we've seen, is so much more than rockets and equations. It is a continuous, breathtaking source of wonder that challenges everything we think we know, a wellspring of mystery that keeps us questioning, and above all, a profound source of humility. It reminds us that our world is a fragile, pale blue dot, a tiny oasis of life and warmth in a vast, silent, and often violent cosmos. The universe doesn't exist for our benefit, it simply is. And in its indifference, we find our greatest motivation: to explore, to understand, and to cherish our unique and precious place within it. The next time you find yourself under a clear night sky, I hope you'll look up with a new sense of curiosity. See not just pinpricks of light, but distant suns, swirling nebulas giving birth to new worlds, and the faint, steady gleam of planets we have visited with our robotic ambassadors. Remember that the sunlight warming your skin is thousands of years old, that the ground beneath your feet contains atoms forged in stellar explosions long before our sun was born, and that the simple human act of looking up and wondering is what connects us to every explorer, dreamer, and scientist who has ever lived. This conversation doesn't have to end here. I'd love to hear which of these 30 facts resonated most with you. Was it the heartbreaking story of Laika, the first Earthling in orbit, the haunting image of the pillars of creation, a monument that may already be gone? Or perhaps the delightful absurdity of a planet so light it could float in a cosmic bathtub? Share your favorite moment from our journey in the comments below. Let's keep the sense of wonder going. If these glimpses into the weird and wonderful universe have sparked your curiosity, then you're exactly the kind of person this channel is for. Consider subscribing and hitting the notification bell so you don't miss our next adventure. Together, we'll continue to pull back the curtain on the greatest mysteries, because as we've seen, the universe has been keeping secrets, and it's just waiting for us to ask the next